All right, hello everyone, welcome back. This fourth lecture is going to be a short one, and we're going to cover proxies and caches. Last time we talked about stateless services, which kind of relates to the topic of caching today. And we showed how the definition of stateless and stateful related to whether or not there was like long-term memory in the in an application. So we showed that it's beneficial to not have state in an application if we wanted to scale it up, have many clones running in parallel, because that allowed them all to be equivalent. If none of them have memory and they don't change over time, they're all equivalent, and any one of them can equally well handle a given request that comes in. Of course, the service as a whole is going to have state. If you're doing anything interesting, like on Wikipedia, users edit articles, those changes need to be remembered. If you're implementing a game, that the game state changes, you need to be able to remember that and show the progress to other players of the game. So to solve that problem, we use a combination of databases and cookies for if we're thinking about a web application, to take the state of the application and take it from your main code and push it down to a database and up to the client and cookies. So this allows us to achieve parallelism and distributed execution in the main application level, and avoiding difficult coordination problems in that level. Instead, all the coordination is handled mainly by the database, and we assume the database is going to be scalable. We'll talk a lot more later on about scaling databases. And so this was the first lesson of scalability. If you can achieve it, it's better not to share data. That just makes things a lot easier. So the first topic of today is proxies. So proxy is a generic word, like in English, which refers to something that does an action on your behalf or on someone else's behalf. In the case of a server, a proxy server is an intermediary for a request. So I have these two hand-drawn pictures here where originally you had a request going into an application and you got a response. This is like a basic high-level view of a service. If we add a proxy in front of that application, we have the request going to a proxy. The proxy hands that request over to the application generates a response, and the response gives it back. So if the application is stateless and the response depends entirely on the input, then for a proxy to be able to handle a request, all it has to know is who it needs to hand it off to. And, well, I mean, even if it is stateful, it could still do the same thing. But if it's stateless, then it can choose between many different copies of an application on the back end, and in that way implement a load balancer. So we'll see this is useful for two reasons. Like, it seems like we're just complicating our system. Like, why have this sort of box in the middle that's just slowing things down? Because it does, in fact, slow things down. It's simpler to have the application go straight to the back end in the simple case. But there are many reasons why this would improve performance, even though it's adding an extra step. Two main reasons. So the first is if we want to implement some kind of load balancing. We'll talk a lot more about load balancing in a couple more lectures. But think about the horizontal scaling I talked about in the last lecture, where we had lots of instances of an application. So for running Wikipedia, we have a lot of servers that are running the MediaWiki application. We want the users to be able to reach any one of those instances, but we want users to be able to go to a single point of contact to start off with. Like, they enter just the domain name, wikipedia.org or en.wikipedia.org. That goes to one place. So that one place can be a proxy, and that proxy can hand off the request to one of several different copies of an application server to generate the response. And if there's a lot of work involved in generating the response, the proxy doesn't have to do that work. All it has to do is hand off the requests and responses. The applications do a lot of work, so it allows one load balancer proxy to handle the traffic for like maybe 10 or 20 or even 100 different copies of an application server. Now, a second reason why we would want a proxy is for caching. And the Wikipedia example that I'm showing you again has both load balancing and caching. I'm going to focus on the caching part of it for now. So on the right-hand side, we have these blue circles are the Apache servers that are running the MediaWiki application. So this is the actual like code of Wikipedia that has the logic for generating pages and handling edits and everything else like that. But in front of that, so what that application does is it's a specific type. It's an implementation of a web application, so it runs on a web server. So the requests that go in are HTTP requests, and the responses that come back are usually HTML pages or maybe images or other things that the browser would want to render. So I said last time that in front of that is a caching proxy layer, which is optional. It's not required. I'm going to explain in this lecture about what the purpose of this caching layer is and also why it's optional and can be removed. So in front we have the specific software. It's an open source software that's running here. It's called Squid, these red cones. Squid is a caching proxy. So a proxy, like I was just saying, is a service that doesn't really have any logic in it. It doesn't have any complex code. It doesn't, like, you don't edit the proxy. All the proxy is doing is accepting requests and handing it off to someone else. You just have to configure the proxy to know what the origin of the data is, where it can turn to send the requests that it gets to be serviced by someone else. So in this case, requests come in from the browser to Squid. Squid hands off the requests to these Apache servers. And the reason why these are here as an intermediary is for caching. So caching, a cache is a storage of recently retrieved items that can be reused. So in this case, what we're storing here are HTTP responses, which correspond in general to web pages on Wikipedia's website. So if someone fetches, let's say, the Wikipedia page for a popular entity like United States of America, let's say, there's a Wikipedia page for that might get a lot of traffic on a day. The first time that happens, the request comes in, it goes to one of these caching proxies. The caching proxy will check to see whether it has in its memory any record of a copy of that document that it has that it can give. If it does, then it gives it back immediately. If not, it turns around and forwards the request to these MediaWiki servers that can generate the article for United States of America. And then it'll return it back, but then after returning it back, it also stores a copy here so that later on, if someone else requests the same article, and of course, all that these because it's using HTTP, which is a like standard protocol, the Squid software can easily look at the request and recognize that it's fetching the same URL. If that's the case, and it'll see that it has a copy, and it can actually return that immediately. So this allows this front end layer to handle a lot of the requests directly without having to turn around and hand them off to Apache. I said that the proxy was an intermediary that hands off the requests, but if it's a caching proxy, then it will actually remember the old responses it's given and repeat those whenever it can. Okay. Now, so for a website like this, that works well. So the unusual requests are not going to be present in the cache. So if you visit a page that's not very popular, generally no one else will have visited that recently, so it won't be in a cache, and you have to turn around and send it to MediaWiki. So this allows less traffic to be sent to this MediaWiki layer, even though there are 200 servers here. By having these caching proxies in front, we are able to reduce the load on those 200 and have 200 instead of, let's say, 1,000 or 2,000 of them. Okay, because we're eliminating duplicate work, basically, because we know a lot of the requests are going to be to the same pages. We are able to replay them. So I'm going to kind of define a cache in general, in case you haven't seen that, because it's an important concept for scalable systems. So a cache is a generic concept that applies to these web systems, but it also applies to computer memory, file systems, databases, and other stuff. Anytime you have some kind of data access and you want to improve the performance of it, and there's like a subset of the data that is going to be used more frequently than the whole set. And also, crucially, so what we do basically is we have a small storage that's called the cache that stores the stuff that you are using now or most recently. And because it's smaller, we assume that it can be faster. Okay, so you can use a technology that's faster because it's smaller. So like, for example, main storage might be on a spinning disk, which has high capacity but is slow, whereas the cache might be in RAM, in memory, which is fast, or if main storage is an SSD, that's faster. You could have something even faster for the cache, like memory, or the like CPUs have caches on the chip to store the recently used memory that's off chip. In general, the smaller you make a storage element, the faster it can be, because there's less area to scan sort of physically, and you can put it closer to the place where you're using it, which is usually the CPU. Okay, so the cache usually stores the most recently or most frequently accessed data. And in this picture, I'm showing it I'm showing it as like an alternative data store that the client can use to store those things that it's going to use most frequently. So the cache is smaller than main storage. It can't store everything in the data set. If we did make the cache big enough to store everything, it would be the same as the main data store, and it wouldn't be any faster than the main data store, right? So by definition, the cache is smaller. And again, because we make it smaller, there's a performance benefit. If you're using a technology where making something smaller doesn't make it faster, then there's no benefit to having a cache. But it just so turns out that with basically every type of storage technology we have, whether it's memory on chip or flash or rotating disk, with all of our storage technologies that we have, making something smaller allows us to generally move to a different, more expensive technology that is faster but has less capacity. Okay, so when we're reading data in a system that has caching, what we do is check the cache first. Hopefully the data will be there. That's called a cache hit. In that case, you return that data. You have it in the cache. You also make a record that entry was accessed recently, because generally you want to store the most recently accessed elements in the cache. That will lead to the best performance. If the data wasn't in the cache, we call it a cache miss. In that case, you have to turn to the origin, which is like the main data store, get the data, and then store it in the cache. But also, usually to do that, we have to evict something from the cache to make room for it. Because the cache is small, generally the cache is always full. So we have to choose something to evict to make room for the new data. Now, I want you to stop and think about which data element in a cache should be evicted to make room for this new element that we just accessed, that we suspect this new element we're accessing, we're going to access it again recently. This whole concept of a cache works because of the principle of temporal locality of data access. Like in general, in practice, data that you accessed recently is likely to be accessed again recently, whereas data that you have not accessed in a while is less likely to be accessed next. Like if you had to guess the next data that you're going to access, your best guess would be the thing you just accessed or something that you accessed recently. That's just because code tends to manipulate variables like repeatedly, right? Or so on. Okay, so which data element should we evict then to make room for the new one? Well, generally the best approach is to choose the least recently used element for the reason I just said, because of the temporal locality of data access. There also is spatial locality in data access patterns generally. So if you access data in like this location here, it's likely that later on you'll access a data location nearby. So some caches, like CPU caches, when they cache memory, will cache in like a whole chunk of memory, even if you just access one piece of it, because it kind of assumes it's likely you're going to access the later parts of it next, and that allows you to like preemptively put stuff in the cache, which is called warming a cache. Cool. So what I talked about so far was a managed cache on the left-hand side, this design where you have some client of the cache that it has code that accesses two different storage systems. One's bigger, one's smaller. It puts everything in the big storage, but it puts some things that are most recently used in the small thing that's fast, and that's a faster storage system. So in a managed cache, the client has direct access to both things, and the code of the client is responsible for implementing caching logic. And in this class, in the systems we'll talk about here, like sort of like web scale systems, managed caches include Redis and memcached. These are basically like databases that are designed to be connected to from your client and that are separate from your main database. So you have kind of like two databases. One is small and fast, Redis or memcached, and that is like an alternative to your main database, which is slower. Okay. There also is another notion of transparent caching, which is when the client is not really aware that caching is happening, but it happens through a proxy. And that relates to the topic of today's lecture, which is this web caching layer that sits in front of, for example, Wikipedia and a lot of other web applications. So the client, which might be a web browser, makes a request to some system, and that system has its own storage, and it gives a response either by using its cache or by turning around and fetching the data from some main storage system, the origin. So caching, so this whole system that includes both a proxy and a origin with main storage, with all the storage, this whole thing is kind of a black box to the client. The interactions this client has with the system could have gone directly to the main system or to a proxy in front of the main system. It doesn't matter. The client doesn't implement any logic for caching. The caching is handled by this proxying layer. And so this is a transparent cache. It's called transparent because the client doesn't know what's happening. The client doesn't see any difference in behavior with this being present versus it not being present. Okay, so the Squid HTTP caching proxy is an example of this. Content delivery networks are another example that we'll talk about later, which is even more clever way of using an HTTP proxy and cache, except it's like globally optimized. And then other systems have transparent caches, like a CPU has a transparent cache from the perspective of your code, because like your code accesses memory locations, but the CPU is actually unknown to your code, is migrating data from main memory to its L1 cache, L2 cache, L3 cache, and so on. Your code doesn't manage that migration of data from memory to cache. Same thing is true of database servers. They have a lot of storage. They have caches in memory to store the recently used data. Operating systems, the file systems in operating systems, like on your laptop, has a transparent cache for accessing files on disk. So it's kind of slow to access files on disk, but the recently used segments of files are stored in memory so that you can modify them quickly, and later on in the background those are like written back out to disk. So that makes the file system performance seem really fast because you're really doing the operations in memory. But you would learn about that in an operating systems class. That's a cool topic. Okay, two different types of caches. So now looking back at Wikipedia, we put this caching proxy layer that's implemented by the open source Squid software in front of the application. I want you to, I'm claiming that this front-end cache is going to handle roughly 90% of the requests without having to touch the database, which is actually not even shown but off to the right-hand side of this. So why is Wikipedia able to handle so many of these requests from its cache in memory quickly without running any code or without hitting a database? Why is Wikipedia able to handle like 90% of its requests from its cache? I have two questions I want you to stop and think about. That's the first one. And the second one is, what is the downside of this approach? Like, what price do we pay for this efficiency of handling 90% of the requests up here without having to turn around and hit the application in the database? Okay, so stop and think about that. That's kind of complicated. Two different questions. Okay, so I have slides to address each of these two questions. The first one we're going to talk about, I think, is the why 90% of the requests can be handled from the cache. And I alluded to this at the beginning of the lecture. It's due to the traffic distribution pattern of Wikipedia and indeed most services. So there's a long tail of traffic on Wikipedia, and I guess the opposite of the long tail is over here, and the rest of it is up here. So what this plot is showing is the frequency of access of different pages on the y-axis. On the x-axis, we have each page listed in order, where we have the most popular page on the left and the least popular page on the right. So what this shows is there are a few pages on the left that have really high frequency of access. These are the popular pages. Like I mentioned, the example of like United States of America Wikipedia page, something that a lot of people will be looking at. But then that drops off, and we also have a ton of pages. The long tail here, this yellow part, the long tail are the pages that are very infrequently accessed. So your database has to store Wikipedia's database has to store all of the articles, right? So the size of the Wikipedia database, is roughly, if we assume the articles are all the same length on average, which we can kind of assume, the length of this x-axis is the size of the database in total. But if we take a subset of that database, the most frequently accessed pages, and put those in cache, so this green part, if we have a cache of this size here, then that allows us to store the most, just a small fraction of the pages. But if we take the area of this green part of the curve, that could be 90% of the total area. So the area would be the frequency, like the traffic. If you integrate this, you get the total traffic on Wikipedia. That green area could be 90% compared to this yellow. I mean, in this picture, it's roughly 50-50 or like 60-40. But in general, this long tail is going to be really thin, really low, and this popular part is going to be really big. So it actually is going to be even more extreme than what you see here. Okay, so we want to optimize the system's performance for these really popular pages, because not because those visitors are more important than the others, but because we can very easily and cheaply handle those requests. If we can, with little effort, with little memory, handle 90% of the requests, then we should do that. And sure, for the 10% remaining requests, the overhead of handling them and maybe the delay of returning the response is going to be longer, and the overhead is going to be greater. But we have successfully reduced our cost, both in terms of the resources we're using and the response time. We've reduced our costs for the 90% of the requests. Okay. Now, if Wikipedia's access pattern did not look like this, if it was kind of flat, where there were let's say 10 million pages and each one of them got an equal amount of traffic, then caching like this would not work well. This architecture is specifically designed for a system that has a long tail of traffic. And now, actually, one thing you can stop and think about now, I don't have a little prompt, but you should stop and think, what is an example of a different application that does not have a long tail of traffic? Instead, it has more of an even amount of traffic across all the data in the system. Well, I'm not sure there are any that are perfectly even, but if you think about, for example, a social media application, you have a lot of data, like Facebook. You have a lot of data and a lot of photos people have posted and stuff. So that if the X is the users and the Y is the frequency of access of the user's data, it's kind of flat. Any given user's data is accessed by a few dozen friends, frequently. And so you need a different kind of architecture to support feeding those, sharing those little bits of data to a lot of users. Of course, there are a few celebrity users on the social media platforms, and for those you can have some kind of caching, but then you still have a huge amount, 90% of your traffic, I guess, on Wikipedia, something like that, would be viewing not celebrity data, but data from your friends, from people who are on a long tail that is actually the dominant part of the traffic. Okay. So the second problem I asked you to think about, or the second question I had for you 2 slides ago about caching, I asked what is the downside of caching? What problems are we going to run into when we start caching data? Instead of getting the latest version of the article from the database, we're using a cached version, so a version of the article that was returned to someone else recently. Okay, so what happens when data changes? We're going to have out-of-date copies that are cached. So I just gave user A a copy of the article for United States of America. User B comes in and fetches and makes an edit to the page. User C comes in and asks to load the page. How do I actually get them? Are they going to see the same page that user A saw because it's stored in the cache, which is an old version of the page, or are they going to see the latest version of the page? How do I solve that problem? Please stop and think about that. there are a few different solutions, and there's no perfect solution. There's a set of trade-offs here. Like if you actually want everyone to truly get totally up-to-date versions of the data every time, then what you really need is the second approach, which is called a coherent cache. And there's a lot of performance overhead for that. So whenever there's a change in the data source, that data source has to like broadcast to all the places that are storing copies to tell them to invalidate the data that they have. And if you do that, then your cache is coherent. So the same data is stored in every part of your cache. Your cache is also the same as the main data store. That is like makes your that's a good behavior to have, but there's a lot of performance overhead in broadcasting those updates. A simpler approach is to just allow the out-of-date pages to be returned, not forever, but for a certain amount of time. So you have a time to live for your cached data, and after that amount of time, your cache contents expire. So you store stuff in your cache, but let's say you only store it for 10 minutes. So for Wikipedia, that might make sense. You store an article for up to 10 minutes. Over that 10-minute time period, if it's a really popular page, that could be really useful. Like you might still have like 1,000 or 2,000 users request the same page over 10 minutes, right? So you've just saved 999 requests to the database. But after 10 minutes, when the next request comes in, even though you have a copy of that article, you don't return it because you know it's too old. You suspect that maybe it's out of date, so you throw it away and you actually go back to the data source and get the latest version and put that in your cache. Okay, so that's cache expiration. A third approach, which is a little bit more subtle, is to never change your data and actually force the user to have some way to update to request a new version of the data. So versioned data, this doesn't always work. Like for example, for a web page, this doesn't make sense, but some databases support this. Like if you have image files, let's say, that are being stored in a storage system and you're caching them, when you update the image file, instead of rewriting the image to the same file name, you can write it to a new file name and then kind of update the logic to have your clients request a new file name instead. Of course, how that happens depends on the details of your application. I guess for now, the things to really... The main strategy we're going to be using in this class is expiration, assuming that caches store data for a certain amount of time before clearing them. Because in practice, that seems to be the most, for these like web scale caches, that's definitely the most common approach, because the coherent caches have too much performance overhead. Coherent caches are used for CPU caches that are transparent, because if you're writing a program that accesses memory, you don't want, like your program would break if it accessed old versions of memory locations. Okay, so for the Wikipedia example, we're talking about a web server, so it's using the HTTP protocol for browsers to specify what documents they're fetching and for the server to give their responses. HTTP is really supports caching well. It's built into the protocol, actually. So the fact that HTTP is stateless means that it makes caching easier, because the same response can be saved and reused for any repeats of the same request, right? So the response depends only on the request. HTTP also has different methods that have well-defined limitations and specifications. So there's like the GET request, POST, delete, and if your application is just getting data, is fetching data, is not modifying data, then you can use this GET method in the request, and then a caching proxy will know that this can be cached because it's not modifying data, or it could potentially be cached. Whereas if you are using a put, post, or delete method, that actually signals that you're modifying data, and so that definitely should not be cached. If you call a delete twice, it should be repeated, I guess, unless it's... We'll talk more about this actually in a later lecture with idempotence. It's a little bit more subtle than that. HTTP also has cache control headers, which are like a standard way for the client and server to enable or disable caching, and also to control expiration time. So when you develop a web server that's returning pages, in your response, when you can set these cache control headers to tell any proxy or client how long, whether it should cache the response and for how long it should cache the response. And this was built in even in the early days, because it was a very useful feature for web browsers. So if you're on a web page, like if you're loading, let's say you're on eBay.com and you're looking through different auctions and whatnot, your web browser is going to fetch like the logos for different parts of the page and like images for buttons and stuff. Those are going to be repeated as you go through different pages, and even on the same page, you might have a repetition of the same little like logo icon, little icon in different places. So instead of having to build into the language HTML some way to like repeat the same image, HTML specifies a URL for the same URL repeatedly, and technically the web browser could fetch those those images repeatedly, but the caching built into HTTP allows the browser to actually keep a record of recently stored fetched images, let's say, because that's a very popular kind of cached object, and use the previously fetched image when it's repeated later. That also applies to CSS pages that are the same as you move throughout a website, and JavaScript also can be repeated, so you don't have to fetch that anew every time. So this feature was really built in with web browsers in mind, but it also allows caching proxies like Squid to do the same kind of caching. And this can be added transparently. So caching with HTTP can be added transparently either at any point between the user interface and the server, because of this deep support for caching in HTTP. So looking at Wikipedia, this is a repeat of the view I showed you before, but now we should understand better what is going on here at the front end with this caching proxy layer. Now, in this final picture, there actually are 3 different layers of proxies. They're not all caching proxies, but 3 different layers of proxies. Remember, a proxy is something that accepts a request and hands it off doesn't know how to fulfill it itself, except it knows who to ask to get the response. So it relays the request to someone else to get the response, and then relays the response back. It's an intermediary. Can you find 3 different layers of intermediary here? Stop and think about that. So I would list these 3. So first of all, we have 2 different load balancers, actually, and we haven't talked too much about load balancers yet, so it's okay if you missed those. But when the request comes in from a browser, it goes to a load balancer, and the load balancer chooses between a set of different Squid proxies to hand the request to. That is a kind of proxy. The Squid proxies are also are proxies because they either hand the request off to this Apache layer or they handle it themselves. When they do hand it off, they're acting as a proxy. At the MediaWiki layer here, the application layer, there also are load balancers. So the request, when it comes in here from Squid, it goes to a load balancer first, and the load balancer decides which of the 200 different instances to hand it off to. It doesn't, but the generating the request happens here. Now, you might have thought that this Apache layer is a proxy because it sits between Squid and the database, right? Because there is a flow of data between the client making the request through this application layer to the database, and the data comes back and it gets returned. Why? But I wouldn't call that a proxy. Why is this, even though it's functionally between the database and the user, why is the application layer here not a proxy? I want you to stop and think about that. Well, the reason is because what the database is, the database is supplying data, but it's in a totally different format. So this Apache layer is not taking the request that came in and literally handing it off in the same format to the database, and the database returning. This database doesn't return HTML that is literally handed back to the client layer. So there's definitely interaction here of fetching data, but this Apache layer does a lot of transformation of that data, and it could make multiple requests to the database to build a page. So there's an interaction here, but it's not a proxying interaction. So we have layering here where this is in this Apache layer where the MediaWiki is in front of the database, but it's not a proxy because it's not just literally handing things off and then relaying them back unmodified. It's doing a lot of manipulation and logic to modify that data and also make multiple requests and all that stuff. Okay, so it's not a proxy layer. Cool. All right, so to review, today I introduced proxies and caching. Proxies are intermediaries for handling requests. They're useful both for caching and load balancing. We'll talk about load balancing later. Today was about caching. Caching is useful because a lot of times services have a few popular documents that can, and if you can lower the costs for those or increase the performance for those, you benefit like the majority of the users. And allows you to improve the performance of your system, lower the cost of your system dramatically. So like for the Wikipedia example, without the caching proxy, we might need like 10 times more application servers. So we cut our costs dramatically by having a caching layer. The caching layer, we can handle a lot of requests with a few servers because the caching proxies are not doing much work. They're not running code. They're not hitting a database. They're just like storing data and returning it back literally as it is received. So those can handle a lot of requests efficiently. We mentioned that HTTP has built-in support for caching, which was leveraged particularly by Wikipedia in adding the Squid proxy. And we'll see later on, we also do HTTP proxy with content delivery networks. Cool. So that was a short one, but I thought it was useful. I hope it was useful, and see you later.